feel free to take it away, Nichole.
All right. So welcome everyone to session 6. This is a first in a series of sessions on the Milky Way, galaxies, and clusters, and pretty much everything in between. So this session, like all sessions, will go for 2 hours, after which we'll have a coffee tea room for some more informal chats or social catch-up. And just to remind you, you can ask questions at any time in the Q&A box. And at the end of the talk, if you want to ask your question directly, go ahead and raise your hand and I can unmute you so that you can ask the question for yourself. So first up, we have our invited talk of the session from Natasha Hurley-Walker. She's going to be talking about supernova remnants at low frequencies. So Natasha, if you want to go ahead and share your screen and take it away, that'd be great.
Okie doke. Can you see that? And hopefully without any Zoom baggage over the top.
There appears to be some Zoom baggage over the top, yeah.
All right, how's that?
Great.
Okay, awesome. Well, thanks very much to the organizers for inviting me to give this talk. I have been working in the field of supernova remnants for 12 years now, but I did have a very long gap while I came here and to Australia and helped commission the MWA. So a lot of my talk is going to be focused on work with the MWA, but I'm also hoping to talk a bit about results with LOFAR as well. So I'm going to give some context about supernova remnants. Why should we care? How should we find them? And then at the end of the talk, I'll explain a bit about what I see as the future of this exciting field. So, kablamo! Starting off the day with a bang. When a massive star ends its life in core collapse, or a white dwarf accretes from a binary companion and accumulates layers, you get a supernova. And the shockwave that moves off from the supernova is moving at a few thousand kilometers per second to start with. And this slams into the surrounding interstellar medium, deposits a huge amount of energy, also releases a lot of neutrinos, although I won't talk about it in this talk. And over time really changes the nature of the ISM around it. The supernovae, they start with a period of free expansion, and then we move into a second phase called the Sedov-Taylor phase. And then finally, the supernova remnant is just driven by its outward momentum and finally dissipates into the ISM. So this takes about a few 100,000 years. And while this is happening, we are usually able to detect them. So why should we care? Well, one of the most interesting questions that's being asked at the moment in the field is what role supernova remnants play in the acceleration of cosmic rays in our galaxy. So the typical picture that's been understood for the last 50 years or so is that diffusive shock acceleration at the shock fronts of the supernova remnant accelerates the charged particles, and there are various mechanisms by which this can generate cosmic rays. So you can end up with the high energy electrons inside the supernova remnant generating inverse Compton scattering on the ambient radiation field, and this can produce gamma rays. You can end up with proton-proton interactions inside the supernova remnant generating pions, which then decay to produce gamma rays. And you can have the shock front interacting with dense molecular clouds, which produces gamma rays as well. So the two latter, the first and third scenarios, you have a way of accelerating cosmic ray protons. So, and yet in all three scenarios, the thing that you see is gamma rays. So there's a bit of a question when we see gamma rays in the galactic plane, what is actually happening here? Are we seeing supernova remnants using any of these three mechanisms, some of which would accelerate cosmic ray protons? And there's a little bit of evidence that pion decay is one of the possible mechanisms. So this slightly complicated plot, comes from a paper from about 20 years ago, looking at on the y-axis essentially the number of photons, and along the bottom the photon energy. And the different dashed line models show different models of what you would expect if one of those acceleration mechanisms was the case. So from the top, the just simple dashed lines, that curve shows purely inverse Compton. Then there's some long dashes which show free, and then there's a dot dash which shows pion decay. And the actual measurements fit nicely on the pion decay option. So there's kind of this circumstantial evidence, but one of the issues that we have is that the gamma ray observations are very low resolution, and so it's hard to pin down exactly which object all of these things are coming from. So there's a whole range of other reasons why supernova remnants are important, which I don't have time to go into, but I've put an exhaustive list and some reading on the left. But I think I've established that at the very least from the cosmic ray point of view, these things are interesting and we should go look for them. So how are we going to go and find them? On the right-hand side, you see two very well-known supernova remnants, which are tied to actual supernovae that we know historically occurred. I think that's Tycho and the Crab. The optical signatures, especially for 1006, are mainly from stimulated emission lines. I think the yellow there is oxygen 3. And it's very easy to miss these things in optical surveys because you're only seeing the filaments of the supernova remnant where the optical lines are simulated. Plerionic supernova remnants, the ones which have pulsars in the middle, are more obvious in the optical. And so you can see this beautiful nebula surrounding the Crab. In the X-ray, these things are also very visible. But X-ray surveys have not always had the resolution, the sensitivity to pick these things up. So, of course, we turn to our friend radio. Now, when I was updating this slide, my original line here said that 95% of supernova remnants were detected in the radio. And that was true until about 5 years ago, but the picture is changing. So I'll talk about more about that in a bit. And the main thing I want to focus on here is that radio is a fantastic tool for finding supernova remnants. They're synchrotron bright, so we see them very clearly, especially as you go to lower and lower frequencies. They can have a range of morphologies, shown here by all the beautiful gallery of things detected by various telescopes. And the kind of classic one that we expect is this sort of shell barrel-shaped supernova remnant, where the shell is expanding outward, and depending on its interactions with the ISM, you can end up with sort of brighter and dimmer areas. And of course, projection effects also play a role. These things are expanding in 3D. The main point here is that we expect from counting high mass stars, from looking at other galaxies, from looking at the star formation rate in our local group galaxies, we expect there to be on the order of 1,000 to 2,000 supernova remnants. And yet are kind of like, absolutely, we're sure about these are definitely supernova remnants. We only know at about 300. So there's a huge gap, and there has been a gap for quite a long time, and so a lot of people are trying to fill it. There's various reasons I've listed on the right why there might still be a gap despite our best efforts. And I would say the biggest thing is that every survey is only sensitive to its particular range of angular scales. So things that are very high resolution tend to miss the larger objects, and things that are very low resolution tend to miss the smaller objects. That's the most straightforward way of looking at it. I put this slide together. This occupied far more of my time than it should have done, but it was just too much fun once I got started. I grabbed these remnant catalogs from the Manitoba Supernova Remnant catalog, and Dave Green's kind of canonical radio supernova remnant catalog. The links are at the bottom left. And messed around in TopCat for more time than I should have to produce this graph of when and how supernova remnants have been discovered. So over time, the very largest strides have been made in the radio, and the confirmed remnants are shown in darker colors. So these are things that we're pretty sure and have multiple telescope confirmations. And but over time, you can see that X-ray and gamma ray telescopes are starting to creep in onto our turf. And so I think this is going to be very important going forward, is the marriage of these high energy instruments with what we're seeing at low frequencies. just to explain on the right, so broadly speaking, the northern hemisphere is more sensitive to stuff on the right-hand side of the plot. And every so often you can see a massive VLA survey come in. So in 2017, you'll see Anderson et al. 2017 pop in a bunch of remnants from the Thor survey. All right, so radio is a great way of finding these things, but the trick is to be sure about what you're seeing. So there were a bunch of bars on that previous chart that were a very pale color because those objects had not been confirmed by other telescopes. And that's because radio astronomers do have a historical tendency of just labeling any circular object that they see in their survey as a supernova remnant. The really key thing is to distinguish between the non-thermal emission coming from the synchrotron of the supernova remnant shell and thermal emission, which could be coming from all sorts of objects in the galactic plane, but quite typically H2 regions. So this slide shows two different examples by two different papers using two different color schemes because goodness knows we're not known for our consistency. On the left-hand side, the radio emission is shown in blue, and the mid-infrared is shown in red. So objects which produce both radio and mid-infrared, like H2 regions, show up as sort of yellow or a kind of purpley red, and some of them are actually labeled, whereas supernova remnant shells show quite clearly as blue without very much mid-infrared emission. And on the right-hand side is the Thor survey, as I mentioned earlier, where the opposite color scheme applies, but the same idea holds true. Things which have just the red emission in this case, i.e. the non-thermal, the radio, and things which have both tend to be thermal, i.e. H2 regions. Yeah, so that's generally how we've been searching for these things. Look, you do a radio survey, look for objects that don't have very much mid-infrared emission. So a recent example is Supin et al. 2018. They looked through the Very Large Array Sky Survey Redux, the 74 megahertz survey, and also compared it to the VLA Galactic Plane survey at 1.4 gigahertz, and also looked at some infrared data from MSX at 8 microns. Now the dashed line there shows a supernova remnant G51.21 plus 0.11 identified by Anderson et al. In 2017. And Supan et al. Argue that actually the supernova remnant itself is just this small blob on the bottom right-hand corner that has this very clearly non-thermal spectral index. And they don't see the rest of the object at low frequencies. So they argue that actually it's a misidentification by Anderson et al. So this ties into what I was saying earlier, which is that when you're doing this work with different instruments that observe different angular scales in a very, very complicated region, it's very easy to become confused. And I'm still not sure which one of these objects is really the supernova remnant. So, slightly tooting my own horn here, but one of the big surveys that's making a difference in this region is the Galactic and Extragalactic or Sky MWA survey, or GLEAM. The key part here is that we've got simultaneously a very wide bandwidth, but also a good access to a huge range of angular scales. So that allows us to not be worried about resolution biases and missing different frequencies at different scales, except for the extremely large scales, sort of 10 degrees or so, and the very smaller scales, our lowest frequency, it doesn't go down to 2 up-minutes, it goes down to about 4. But this is still a lot easier than comparing different data from different telescopes. And if you'd like any of this, then it's available online. The catalog's on Vizier, and there's images on RVO server or Skyview. I did work quite hard to tidy up the galactic plane itself to really make sure that we'd be able to observe supernova remnants and other galactic objects. So you can see the top is some very early data reduction where I wasn't really focused on the galactic plane. And the bottom took a lot more CPU hours and a lot more care and attention to the WS clean settings to get that emission all deconvolved perfectly. So why is it good to see these in-band, this in-band wide bandwidth? Well, I'll just give you a sort of beautiful visual example. So if we just look at one frequency, this is much more similar to kind of traditional radio surveys in the past. You could pick out any number of circular objects here and claim that you've found supernova remnants. But the green circles show supernova remnants that were identified by previous surveys, and people are pretty sure these things are real. However, if we move to the multiband GLEAM view, it suddenly becomes clear that some of the circles that you might have identified in the previous image as possible supernova remnants have a very deep blue color in the wideband view. And the dark blue is coming from a lack of emission at the 88 megahertz channel. And this is a sign of free absorption from foreground H2 regions. So the H2 regions become opaque to the diffuse galactic synchrotron at the very lowest frequencies. And so essentially, or everywhere it's blue, you're seeing a turnover at low frequencies. And this allows us to very, very clearly distinguish between the non-thermal emission, which has this kind of pink color, and H2 regions, which are rising spectrum for us from the very steep turnover, and then they flatten towards the top of our band. Now, this has allowed us to identify lots of new remnants, and I've just highlighted a few there in pink. If you compare these to the infrared, of course, which we should always do, you also see a lack of mid-infrared emission, although wherever it's very complicated, because it's, of course, the galactic plane, the picture becomes less clear. Now, of course, just hand-waving and saying pink things are remnants and blue things are not is not very scientific. So I wrote some software to perform very careful measurements across our full band, really taking into account the background of the local area. So the white annotation on the left shows the area enclosing the object that I want to measure, one of the remnants that I suspect. And the blue dashed lines show where I'm saying, I do not believe that we should use this as a background measurement because it's complicated galactic stuff. So then the light shaded region shows where the background measurement has been made. And so then on the right-hand side, that's just a flux density against frequency plot. The background measurements are shown in red, and the flux density of the object that I'm trying to measure is shown in black. And this allows us to get reliable spectral indices, even despite this complicated background, which is one of the disadvantages of picking up all of the large angular scales. So, sorry, just slide loading, I think. So to show our candidates off in full resolution, and also I'll try and point out the Anderson et al. Release, which is 3 times bigger than GLEAM, so very important, but not quite low frequency. Those objects are shown in red on the left-hand side here, and the GLEAM new objects are shown in magenta. And our sensitivity to large angular scales also allowed us to detect a couple in areas where we didn't really expect there to be supernova remnants. So here's the exhaustive list. This is a review talk, so I'm not going to go through all of our work. But we were able to perform some pulsar associations, and that allows us to get distances, which then allows us to get physical properties. And this is a long-running issue for supernova remnant surveys, is you find these things, but then you have no idea whether they're a big thing far away or a small thing close by. So this is only going to become more of a problem in the future. Now, one thing that I picked out, I thought was interesting when I reviewed the literature from the last 5 years, was that traditional radio galactic plane surveys had usually focused on quite low latitudes, and that often means that you need to use quite a high resolution in order to distinguish all of the different objects, because there's just so much confusion. But in recent years, we've been having more wide field surveys, we've been going to higher galactic latitudes, and we're starting to find these relatively high galactic latitude supernova remnants. So on the left is one that I found in the GLEAM survey at a galactic latitude of -9.7. And on the middle is one that Roland Koth has found with the Canadian Galactic Plane Survey, which is 1.4 gigahertz, so not quite low frequency, but we give them a pass for this example. And on the right is a figure that I would love to have included in full, but I can't for embargo reasons. But we've there's a detection of an object at a very, very high galactic latitude, which is very exciting. So these things are all located in quiet environments, often on the border between the galactic disk and the halo. And what seems to be a trend, although this is just from very small sample size, is they do seem to have much lower surface brightnesses than you'd expect from all the traditional modeling, even if you lower the hydrogen density to kind of rather ridiculously low values. The nice thing is that they tend to have easy polarization to pick up. So we haven't done any polarization analysis on our object because that wasn't part of the original survey. But in the Kothas et al. Paper, the CGPS is able to pick out the magnetic field, and you can see the beautiful shell-aligned magnetic field in this object. So these are really convenient objects because they're away from the rest of the galactic plane. So we can actually probe like the processes of supernova remnants without being confused by all of the different high density and strange environments that can be occurring across the galactic plane. So hopefully we'll get to share that final panel with you in a few weeks. All right, so moving on to some work from LOFAR. This is some work done by a former summer student of mine, Laura Driessen, while she was at Astron for her master's. And they investigated an area of the galactic plane. I think this is with the LOT survey. And they were looking for, they were checking up on some existing candidate supernova remnants detected by Anderson et al. In 2017. So those are shown with the dashed lines, while the known supernova remnants are shown with white lines, and known H2 regions are shown with green. And again, the great thing about low frequencies is you can pick out the thermal versus the non-thermal emission. And they were able to get spectral index measurements of some of these objects and at least confirm one of them, the central one, as a supernova remnant. For 3 others, they decided actually Anderson et al. Were incorrect, and for 2, they were unable to make a distinction. Low frequencies also allow us to derive some insight into the actual astrophysics, and Maria Arias has done some really fantastic work in this area. On the left is shown VRO 420501, which is this kind of famous supernova remnant where it looks as if perhaps the progenitor exploded into 2 regions of different densities, a low density region in the sort of wing area and a high density region that keeps the remnant compact and circular on the other side. The LOFAR spectral indices are not up to much by themselves at the moment. So on the right-hand side is just the in-band HBA spectral index for VRO and also a nearby H2 region. But if you bring in some ancillary data, such as like at 1.4 gigahertz, then you can really get a great spectral index, and that really helps you with the physics. But not only that, while they're not able to do these very highly resolved spectral indices very well at the moment, hopefully the slide loads, they are able to decompose the individual object across the HBA band and also across other frequencies. So with enough ancillary data, they've found that there's this flattening at the higher frequencies of the shell and the wing, whereas at the lower end of the band, the shell and the wing become steeper, while the middle of the remnant seems to have a consistent spectral index throughout. And so there's all sorts of mechanisms that could be producing this. I've listed a couple on the side. I'd highly recommend you check out her paper. It's quite interesting, but there's a lot of different options as to what could be going on here. So getting better spectral indices would really be key to improving this kind of work. And as a little taster, we also found a similar object in the GLEAM survey. So I think that there's going to be a whole lot more of these as we produce more surveys. Now I've just got a minute, so I'll just touch on the synergies between low frequency radio and gamma ray astronomy. So this is a galactic plane view from the HESS system, and this is really probing these very young energetic supernova remnants. If I compare that to the GLEAM survey, it looks completely different. And this is mainly because we're looking at 2 quite different populations. where the low frequencies are more sensitive to these older fading supernova remnants. But as the sensitivity limits of both types of instrument improve, we're going to meet in the middle, and we'll be able to pick up, the low frequencies will be able to pick up more energetic remnants, and the gamma rays will become more sensitive to older populations. There'll still be a lot of interpretation required and probably some modeling. So I just thought I'd mention this paper by Nichole Maxted, where we found a coincident gamma ray source with what seems to be a supernova remnant, sort of a normal canonical shell type supernova remnant discovered in GLEAM. And the localization isn't great, but as far as we can tell, this is more evidence that remnants are accelerating cosmic ray protons. All right, so final stretch. LOFAR is also giving us this tremendously high resolution view. So this is Francesco de Gasperin's recent paper, which covers 6 different 18 sources. And these fantastically high resolution, these are sort of 10 arcsecond level models of Casei and Taurusei are just gorgeous. We're using them now in our calibration and peeling. And they do allow you to do these resolved spectral indices. You've got enough signal to noise on these high sources that the HBA can get enough signal to noise, and you can pick up low frequency absorption, as I mentioned earlier. But this isn't low frequency absorption from H2 regions. This is low frequency absorption from unshocked ejecta inside the supernova remnant. So this is kind of a tomographical view of the remnant. This is really beautiful work. And with increasing telescope power and sensitivity, we should be able to extend this to more objects. So very quickly touch on the future for the field. I think LOFAR 2.0 is going to be fantastic for galactic science, bringing the sensitivity of the LBA in line with the HBA. Being able to observe with both of them at the same time will get you those wideband spectral indices. That's just going to be beautiful. So I'm really looking forward to the instrument session where we might hear a bit more about that. In terms of the MWA, I'm PI of GLEAM X, which is using the extended array to double the resolution of GLEAM and reduce the noise by about a factor of 10. And so these instruments and hopefully some of the other low frequency instruments here will be working toward a complete census of supernova remnants, maybe one day hit the magic 2000. We'll hopefully be able to perform more measurements of resolving unshocked ejecta in lower and lower brightness remnants. This is an object that we're trying to do this with GLEAM, but I think we just don't have quite the sensitivity just yet. And of course, the Holy Grail is being able to resolve properly the source of cosmic rays. And this is just an example of an object found by Hess where I looked it up in GLEAM, and it's just not quite. We need more resolution to really be able to say something about this. Of course, one day we'll have SKA, and that is going to be absolutely tremendous. That incredibly wide bandwidth of 50 to more than 300 megahertz. Going right down to those low frequencies will give us a huge lever arm for studies of low frequency absorption. The southern sky location is important. And as I keep coming back to, not missing spatial scales is just absolutely vital if you want to really understand the galactic environment. So to wildly speculate, if you take all of the remnants that have been discovered over the last 50 odd years and you just plot them cumulatively and you assume everybody was right, you can just fit a line to it. And we're still not there by the time I retire. But no, I suspect with the advent of things like eROSITA and SKA and CTA, this is going to go a little bit non-linear, and we will get to that population census in the end. So I shall leave it there. Thank you very much. And I'm happy to try and take questions. Of course, if it's not on my work, I may not be able to give you the best answer. Thanks for your attention.
Thank you, Natasha. So we have about 2.5 minutes for questions. So please go ahead and type your questions in the Q&A or raise your hand and I will call on you. We did have a question in the Q&A that you ended up answering, but I am somewhat interested to hear if you have any further thoughts on it. The question revolves around, have you detected any examples of resolved thermal absorption against or internal to individual SNRs, and that's from Nimir.
Yeah, so we are working on that that young remnant. Oh, I'm gonna have to dig up the telephone number. Sorry, my laptop is not happy about switching away from the presentation. Just a second. Yeah, and so I'm working on that with Maria and Fabio Acero. Yeah, the signal to noise is a real killer, because in every pixel, every voxel, you need enough that you can fit a spectral index. And so in the galactic plane, you're so confused that it's not just the thermal noise, it's the confusion noise, at least for GLEAM. So we really need to amp up our resolution to do this properly for GLEAM-X. And yeah, I think for LOFAR, the issue is probably the HBA in-band sensitivity and reliability for those spectral indices. And if you need to bring in other data, then you've got all of the same issues that, single dishes don't have the resolution to get past the confusion.
Great. Nimir, did you have a comment on that?
Yeah, thanks for answering that. Just to follow up, there have been a few cases of actually the detection of the resolved absorption, not just in CAS-A, but they're extremely useful because they give you that all-important distance information that you mentioned.
Yeah.
In other words, you can, especially in complex regions, you can disentangle the relative superposition of the remnants from the H2 regions, and in some cases, see that they're interacting, which has always been a very difficult thing to do in galactic complexes. You do have to go pretty low in frequency, though. I mean, I would imagine at a lot of higher GLEAM frequencies, you're not going to see it. But when you get down to low band frequencies, it should be all over the place.
Oh yeah, the LBA is just going to be beautiful for this work. It's been very exciting.
Thank you.
Awesome. So that's great. We've run out of time, even though we have a couple more questions in the Q&A.
Happy
Natasha,
to chat in Slack.
Yeah, that'd be great.
Great.
All right. So thank you very much. Next up, we have Jess Broderick. If you can go ahead and share your screen, we'll get started. Jess is going to talk about a new search for high redshift radio galaxies using the NWA GLEAM survey.
Hi, everyone. Hopefully you can hear me and the slides have shown up okay.
Yep.
Okay. Yeah, well, thank you very much to the SOC for giving me the opportunity to talk. So I'm going to be presenting some research on behalf of an international collaboration studying high redshift radio galaxies. I'll be talking about some of the work that I've been doing, but also work led by colleagues at Curtin, Guillaume Drouat, and Nick Seymour. So why do we want to study high redshift radio galaxies? So if we look at the figure at the bottom left, that's the Hubble KZ diagram. So plotting near infrared K-band magnitude as a function of redshift. It's the radio galaxies that are the most massive galaxies at a given redshift. They trace out the 10 to the 12 solar mass baryonic mass limit. So high redshift radio galaxies really are unique laboratories for studying massive galaxy formation and evolution. So how do we go from systems like the spiderweb galaxy, which I show in the bottom right? So you've got many smaller galaxies merging together, triggering radio emission, the whole complex system enveloped in this giant gaseous nebula. How do you go from a progenitor of a massive elliptical like the spiderweb galaxy to the giant CD ellipticals that we see in the local universe? Now, in our project, we're particularly interested in what massive galaxies can tell us about the physical conditions within the EOR. And there's lots of interesting questions that we could potentially address. For example, like what are the extreme processes that allow supermassive black holes to grow so quickly within the first billion years of the universe? How do the supermassive black hole and host galaxies co-evolve at early times in the universe? Better understanding the processes of accretion and feedback. What are the environments in which these sources reside? What are the roles of magnetic fields? For example, how can they affect the initial mass functions of the first stars? And then how does that subsequently affect the EOR? So potentially there's a lot of really high impact science that we can do with high redshift radio galaxies within the EOR. But first, we need to find these sources, that they're quite rare. Traditionally, they're found via selecting sources with ultra steep radio spectra. Now, it's really in the last 5 years or so, it's deep low frequency surveys that are opening up new parameter space. So for a long time, the record holder for the most distant radio galaxy was at a redshift of 5.19. But recently, work by Saxena et al. Resulted in the discovery of a radio galaxy at redshift 5.72. And that was from ultra-steep spectrum selection, making use of data from the TGSS 150 megahertz survey. The redshift was confirmed with optical spectroscopy on Gemini North. Now, our project uses a somewhat different approach. So we're making use of radio spectral steepness and curvature, and we do that by using broadband data from the MWA GLEAM survey. And then to get redshifts, we take ALMA data and we look for molecular lines. Now, in our pilot project, we've discovered a radio galaxy at a redshift of 5.55. So again, another very high redshift source. And of particular interest here is that our discovery GLEAM 0856 is an order of magnitude more luminous in the radio than the discovery by Saxena. Now, our GLEAM 0856 has been spoken about in previous Science at Low Frequencies conferences. I just note, though, that since the last meeting, the paper on our pilot sample has now been published. That's in PASA, so please go and take a look at that. So I'm just going to spend a few slides now on work that we've done on our pilot sample sources since the last Science at Low Frequencies conference. Now, one of the other very interesting sources in the pilot was GLEAM 0917, what we've termed the oddball. Now, the initial work during the Druart et al. Study suggested that this radio galaxy might be at a redshift of 10.15, which would be extremely exciting. Now, in recent times, we've taken ALMA and JVLA DDT observations to try to confirm the redshift. That was based on relatively weak CO lines, as you can see here in the figure. Now, on the basis of the higher signal to noise data from the DDTs, unfortunately, no molecular lines have been detected. So that's in disagreement with our original interpretation. So this source is rather mysterious. So we've put all the information that we have together about our oddball source in this plot on the right-hand side. Now, this is probably a conference talk in itself, so I'm not going to go through it in detail. We can chat about it on Slack afterwards if people are interested. Just a few key points about 0917. It seems like it probably is a source at high redshift, and if it's at very high redshift, it's a very massive system, and it will challenge galaxy formation evolution theories because you have to get a lot of mass in place in a very short time after the Big Bang. It's also a very compact source. It's probably only a few kiloparsecs in size, so it's very similar to the discovery by Saxena. It's not a particularly gas-rich system. It doesn't have a large molecular gas reservoir, as some other systems at high redshift have. It doesn't seem to have much dust either, which is interesting. Another thing, we still have a few redshift coverage gaps, even with our DDT observations. There's also a larger gap at low redshift, but I think it seems unlikely that the source is below a redshift of 1. So yeah, if you want to chat about this more afterwards in Slack, I'd be very happy to do so. This source is also a very radio loud object. If you look at the plot at the top there, that's the ratio of the low frequency flux to near infrared flux. And the orange line is for 0917. So it's got an extreme flux ratio. So it seems like this is quite an interesting source. And we've recently obtained the first of our data sets from the Hubble Space Telescope to try to unravel the mystery here. We've detected the source in the F105W filter. That's the image at the bottom. So we've got a detection there. It's just to the left of the centroid of the ALMA contours. There's a little bit of extension as well that you can see, which could potentially, for example, be extended Lyman alpha emission aligned with the jet. Now, the photometry from Hubble combined with our K-band detection of this source suggests that the galaxy could be above a redshift of 7, somewhere potentially between a redshift of 7 and 9. That will, of course, be very exciting. But stay tuned. The spectroscopy that we're getting next month will confirm that. So yeah, let's see how that all goes. But yeah, fingers crossed. A radioluminous object at those redshifts would allow a lot of very exciting science to be done. So also we've done a LOFAR low-band observation campaign for GLEAM 0856 and 0917. We've obtained 21 hours worth of data between 34 and 66 megahertz, so going lower than GLEAM to constrain the low frequency spectrum to search for a spectral turnover to see what the mechanism is and then try to understand the underlying physics. So you can see the SCDs there on the right from the Druart et al. Study. The solid line is it's a triple power law fit. The dashed line is a double power law, and you can't distinguish between the two at the low frequency end. The uncertainties there are in purple. So the low frequency data that we can get from LOFAR is really important here. So I've reduced the data using prefactor on the Cyro cluster PSC and done imaging with WS Clean. And I'd like to present some very preliminary results. This is still very much work in progress. So LOFAR LBA observations are in general technically challenging, but now we're going to the equator, so that exacerbates the technical challenge even more. But I'm very pleased to say that we've detected GLEAM 0856, our redshift 5.55 radio galaxy, all the way down to 36 megahertz. So the signal to noise, even just using a small amount of the bandwidth, around 36 megahertz, we get a signal to noise ratio of 20. You can clearly see it there in the center of both images, at the bottom of our frequency range and at the top. At a fairly moderate angular resolution, but that's enough for us to do some interesting science. So this is a very promising start to the analysis of this LOFAR data. Now, if we take various small megahertz chunks across the bandwidth and then add that to the spectrum that we had before, there's very tentative evidence of a spectral turnover at 40 megahertz, which corresponds to a rest frame of 260 megahertz. So yeah, this is sort of, it's at an early stage. The next thing is to try to work out whether that could be synchrotron self-absorption or free absorption. I note with interest that the LOFAR 64 megahertz flux seems to be between the GLEAM 76 megahertz flux density and the VLSSR flux density. Now, many people have spent a lot of time trying to understand low frequency flux scale accuracy. For example, Natasha Hurley-Walker and collaborators spent a lot of time doing careful checks for the GLEAM survey. So I just note with interest for now that the LOFAR flux may be in between the VLSSR and the GLEAM fluxes. Although having said that, if you take the GLEAM fluxes and you predict what the flux should be at 64 megahertz, it's kind of roughly the right value with quite a bit of scatter. But there might be some interesting work to do here as a test case for low frequency flux scale accuracy, in addition to some of the science that we want to do as well. So we've got some more data to process as well. This is with 3 of the 7 runs, but already I think a very promising start. And we also see our oddball source all the way down to 36 megahertz as well. So again, some very preliminary images. One might ask for this source whether, if it's an extremely high redshift, whether we'd see a turnover in the LOFAR LBA band. If you take the work that Joe Callingham and collaborators did with the MWA for peak spectrum sources, and you look at the rest frame turnover frequencies, having an observed frame turnover frequency between 34 and 66 megahertz, is indeed plausible. And we kind of already see that with 0856. If this source is, for example, embedded in a very sort of dense ionized bubble at extreme redshifts, that might actually help us too. So if you had a free absorption turnover, if you take the Bremsstrahlung physics, if we simply have a very dense ionized environment, it might shift the turnover to slightly higher frequencies, which sort of might help us. So yeah, we're very much analyzing this data at the moment. So stay tuned. We should have more results in the coming months. Okay, so in terms then of expanding our pilot studies, I'll spend the rest of the talk talking about building on the success really of the DRUAT study. So our selection technique is very promising with the caveat of small number statistics, but essentially we may have 50% of our sources from the pilot being at very high redshift. So we want to use the same technique, but also incorporating the lessons that we learned, particularly removing the low redshift interlopers, and then building up the pilot sample over a much larger area to lower flux densities to try to find more of these systems to build up, hopefully, a large sample of high redshift radio galaxies within the EOR. So the survey data that we're using, so as in the pilots, again, we're using the GLEAM survey, and we're also making use of near infrared data from the ESO Vista Viking survey. Some further details here. So we use the GLEAM Year 1 catalog, but also GLEAM Year 1+2 where that's available. That's particularly more at southerly declinations. So again, we've got that wideband coverage between 70 and 230 megahertz. For the Viking data, we're focusing on the K-band data, so that's 2.15 microns, but also looking at the J and H band data as well. The sample is defined over an area that's 25 times larger than the pilot, which was done in the gamma-9 survey region. And we've got two strips, one at equatorial, one at the South Galactic pole.
5 minutes, Jess.
Okay, thanks, Nichole. So the sample selection criteria. So there's a few things that we need to consider here to try to put together a sample to most efficiently find high redshift radio galaxies. So the first are the radio flux densities. So we've expanded some of the criteria here based on the pilot. So we're going an order of magnitude deeper. So if you look at the plots on the right, that's our rest frame luminosity as a function of redshift. So that dashed black line shows that with our lower flux density cutoff, we'd be sensitive to the types of radio galaxies that were found at high redshifts in the Saxena et al. Study. Now, brighter sources can be particularly helpful for H1 absorption studies. It helps with the optical depth sensitivities that one can reach. And also as well, I mean, there are some very brighter radio galaxies above redshifts of 4 with 151 megahertz fluxes above a Jansky. So we're not using an upper cutoff to the flux densities for the full sample. The radio morphology is another key consideration. So as you can see here in this figure, the median projected linear size decreases as a function of redshift. That's the black circles. So essentially what is happening at very high redshifts is that you have significant inverse Compton losses due to the CMB. And so you end up selecting very young, compact radio sources. So, you know, of kind of order of 10 kiloparsecs or lower at the very highest redshifts. And indeed, that's consistent with what we see for 0856 and also possibly for 0917. So we're using a largest angular size cutoff of less than 5 arcseconds. Kind of this youth redshift degeneracy has been discussed in the literature kind of going back 20 years now. For example, the paper by Blundell and Rawlings. The radio spectrum. So if we're in the observed frame and we're observing between two fixed frequencies, as for example, I've indicated in magenta there, the actual part of the rest frame spectrum that we sample very much depends on the redshift, how it's shifted into the band where we're observing at. So in the pilot study, we used the Hergé radio galaxy sample. So high redshift galaxies there, we shifted their spectra to see what the steepness and curvature properties would be at higher redshifts. And essentially, we've defined this parameter space. So alpha is the steepness, beta is the curvature, and we're selecting sources in the bottom left there, delineated by the black lines. So that's where we think our best high redshift radio galaxy candidates are. Now, those black circles in that plot are the known redshift greater than 4 galaxies with GLEAM data. Okay, we can see that our selection criteria selects the majority of them. So yeah, so in terms of curvature, we're fitting a second order polynomial fit, and then we take these criteria in alpha and beta to select our sample. And then lastly, K-band magnitude is also an important consideration. So we want to select sources that are faint in K. And essentially, as shown in this figure here, a faint K-band magnitude cutoff, it keeps hopefully most of the high redshift sources, but removes a lot of the low redshift interlopers. So we're using sources that aren't detected in Viking. So that's 21.2 in the AB system or 19.4 in Vega. And at the bottom, as you can see, the sources above redshift 5.5, you know, they've got very faint K-band magnitude. So we need to use a cutoff along the lines as I've shown here. So we've got lots of sources then to look at, many thousands, but we can make a number of sensible cutoffs to get rid of the interlopers at low redshift. And we can whittle that number down essentially to a number that's manageable to look by eye. And then, so with the help of a third year student at Curtin, Nigel Wright, we've ended up with a sample of 65 sources that are very compact in the radio, no K-band detections. These are our good high redshift radio galaxy candidates that we're following up. And I'm also putting a sample definition paper together. And then just a few final slides. So the moment we're doing broadband SED modeling, so we're getting a lot of compact array data for the full sample. We're observing actually literally right now. Luckily, someone took over the observations before I started my talk. So we're doing 30-minute snapshot observations. We're getting sort of good imaging quality. As you can see in the bottom left, they're compact sources, so the images aren't particularly exciting. And then we're starting to look at the broadband SED. So taking the GLEAM data, literature data, our compact array points, here's two example spectra. You can see here in both cases, the source is steepening as we go to higher frequencies. So there's a lot of interesting stuff we can do with energy loss mechanisms, studying the environment. How does this feed back into the selection procedure, and how can spectral breaks determine jet ages? So I think I'm just about out of time. So it's the next observing campaign. So the ESO and ALMA observations, we have planned to get more K-band imaging and spectroscopy. Unfortunately, the ESO and ALMA cycles have been interrupted significantly by COVID-19. There wasn't a proposal deadline a few months ago. Fingers crossed that we can apply for time in March next year. And I will just leave up my conclusions there. I hope you agree that we've got a lot of very interesting results so far, and hopefully a lot of exciting EOR science to be done with a full sample. So thank you very much.
Thank you, Jess. We have two questions in the Q&A for you. The first one, well, both by Nithya. The first one being, have you estimated the confusion noise in your pixel, and how do you avoid the in-pixel confusion effects from foreground radio sources in the GLEAM data where the angular resolution is about 2 arc minutes? Wouldn't the spectral indices get mixed from the foreground objects if you are relying on USS for the selection?
So I think if I understand that correctly, if this is essentially referring to like source blending at given the low angular resolution of GLEAM. Perhaps we can chat about that a bit more in Slack afterwards. I think the fact that we're getting a lot of higher frequency data points, I think should give us a much clearer picture on the spectral distributions of these sources. So I think we can certainly verify the spectra, the steepness and curvature that we're obtaining with GLEAM with the higher frequency data. So I think it gives a good initial starting point. I mean, the selection technique has already, I think, given some interesting results in the pilots, but yeah, I think there are potentially a few things there that we can look at in more detail. So I'd be happy to chat about that afterwards on Slack some more.
Okay, sure.
And Nithya, you have another question. Do you want to just ask it?
Yeah, I was wondering how you estimated the redshift to be 10.1 for the 0917 when you said that the ALMA lines were not found, and Hubble also suggested it was probably a greater than 7 object.
Oh, okay. So in the original ALMA data that we obtained, there are a number of relatively low signal to noise lines, around a signal to noise of 3. But there are several CO lines. So you can sort of take those positions, and there are various solutions that could correspond to the redshift. I think the most confident one at the time was at a redshift of 10.15. But with the higher signal to noise data, it seems as though those relatively low signal to noise detections in the original data, I mean, the newer data doesn't quite support that interpretation. So in terms of the Hubble data, I mean, that's kind of looking then at the optical and near infrared SCD. So taking the Hubble photometry, combining it with our K-band photometry. And there is a suggestion there based on the magnitudes that the source may be between redshifts of 7 to 9. But again, happy to discuss some more details with you on Slack regarding that.
Okay, thanks.
Thanks again, Jess. Great talk.
Thank you very much.
Now we will move on to Catherine Ross. So Catherine, if you want to go ahead and share your screen and unmute yourself. Kat will be talking about unexpected spectral variability with the MWA.
Thank you, and thank you to the organisers for giving me this talk. It's really exciting to be presenting this research with the MWA. But before I go into this paper, I just want to quickly mention a campaign I'm also running to correct science courses around Australia so that they include a more diverse representation of women. If you're interested in that, please feel free to follow on social media or contact me about that as well. But today that's not what I'm talking about. I'm actually talking about a recent paper that I'm really happy to say has just been accepted in RAS. So this talk is just going to be outlining basically the main results of this paper, but also the methodology and the statistics used in this paper as well. A bit of background first. So active galactic nuclei, it's generally the main phase of active radio galaxies, and they can kind of be categorized based on the fact they have this really bright central region, which is the core where the matter is accreting onto that supermassive black hole, as well as then these extended large radio lobes. The MWA in particular, or these lower frequencies, are really probing the extended structure of those lobes rather than closer into the core. But that entire structure can be hundreds of kiloparsecs in size. So it really extends far beyond the actual galaxy itself. And we generally call this morphology a double or a triple based on sort of how many bright regions we see. When we look in spectral space, most of these AGN follow a really typical a power law SED, so just a straight line in log-log space. But there is a subset of active galactic nuclei, which I'm going to focus in today's talk because it turns out they're actually quite interesting. So peak spectrum sources, you can see here, they have a very distinctive peak in their SED. So it's no longer that power law SED, which is where they get their creative name. And that peak can range anywhere from 100 megahertz right up through to 10 gigahertz. But the peak spectrum sources still follow the very typical shape and morphology of typical AGN, but they're on much smaller spatial scales, so only up to 20 kiloparsecs in size. And in fact, the size is actually related to where the peak is in their spectrum. This is called the linear size versus turnover relation from O'Dea in 1990. So the MWA probing the megahertz frequencies, it's really probing right down in the bottom right here. So these are the more extended of these compact sources, up to tens of kiloparsecs in size. And the higher frequency the peak, the smaller or more compact that object is. A little bit of background on variability itself. There are two main categories, so either intrinsic relating to the source itself, or extrinsic relating to that light being varied on the journey towards the observer, I guess. So intrinsic, there are several different ways that we can produce variability or that we can observe variability. And that comes from right from the actual core itself through to changes in optical depth related to the sort of immediate environment as well. Extrinsic at megahertz frequencies, we're really only going to be detecting two forms of extrinsic variability, and that's interplanetary scintillation, or IPS, which is often on timescales of a few seconds, and refractive interstellar scintillation, or RIS, which is going to be the big factor in this study. Refractive interstellar scintillation, as the name kind of gives away, is related to the interstellar medium in our galaxy, and often occurs on timescales of years to decades at megahertz frequencies. But what's really important about differentiating between intrinsic and extrinsic is they both actually have characteristic ways that they exhibit themselves in the spectra. So they're both showing spectral variability, and being able to determine the difference between the two really comes down to studying that entire SED. However, previous studies into variability haven't quite been able to capture that entire story. So when it was first discovered by Richard Hunstead in the 70s, that was using single frequencies, right through to last year where Martin Bell published the MWA transient survey. So there are lots of single frequency studies, but you miss that entire spectral coverage and understanding of the way that that variability affects the SED. There have been studies that look at the entire SED, so 2018 and 2005, which did look right up to 10 gigahertz, but this was using archival data, so it was not actually sampling the entire SED simultaneously. It was combining multi-epoch data, and it was starting at 1 gigahertz. So you're actually probing those higher frequencies where we tend to expect to see a bit more variability compared to the megahertz frequencies. I want to point out one source in particular, and this is from Stephen Tingay's published paper in 2015, and that is this single source, but you can see in the megahertz frequencies right on the left there that there's really quite a lot of variability in the model based in those megahertz frequencies, but there is variability across the entire SED. So it really shows that the spectral variability is really important for determining what's going on with the variability, but we simply haven't had the technological capabilities to study lots of sources with a lot of spectral coverage that was taken simultaneously. We've really just been limited in terms of the telescopes available. Until now, yay. So the MWA is really one of a kind in this. It does take roughly simultaneous coverage of the SED from 100 to 230 megahertz, at least in the GLEAM survey, which is what we use. So we're using 2 epochs of the GLEAM survey that were taken roughly about a year apart, and that's data work done by Tom Franzen, which has now been submitted to PASA. And so we take advantage of these 2 epochs to try and see what's going on within the MWA band between these 2 years. This survey is focused around the South Galactic Pole, covering about 8,000 square degrees. So we really have quite a large region of sky, as well as spectral coverage, and that's taken roughly simultaneously. So it's really a one-of-a-kind survey that we haven't really been able to do before. So the actual data that we're studying, after a few quality controls to make sure that we're really confident with the sources that we're studying, the variability that we're detecting, we're surveying around 21,000 sources. And I want to point out a subpopulation in particular, and that's the peak spectrum population, where we find over 400 sources in this survey. And those are sources that have the same quality controls as the master population, but have also followed the same criteria that Joe Callingham outlined in his 2017 paper. So these are just sources that have a peak in their spectrum as well. And what do we find? Well, the vast majority of sources look pretty much just like this. There's next to no variability. They follow a typical power law SED, and that's exactly what we'd expect from AGN. They're too large to really be showing too much variability on this timescale or even on human timescales. So that sort of all makes sense. And even if we look at peak spectrum sources, we see that they still maintain their peak spectrum and show little to no variability as well. So things are sort of behaving as we expect. But I guess, spoiler alert, the title of my talk kind of gives away that there must be something else going on. And indeed, we do see sources that are peak spectrum, but in the following year in that blue SED, you can see the entire SED is shifted upwards. We also see sources that were previously peaked in the first year, and then we return in the second year and they seem to lose that peak spectrum classification, or that peak is seriously diminished compared to the other year. We also see the reverse of sources that weren't particularly peaked, but have a now much more pronounced peak in their SED. So it seems that not only are things varying, but having this spectral information means that we can see things are varying in very different ways as well, which means we're really tasked with a problem of not only detecting that variability, but classifying it. And since we now have a population of 21,000 sources, it's no longer viable to just be going through by eye and selecting things just judged on by eye assumptions. So that's where we present the variability index parameter, or the VIP. So the VIP is a statistic based on the chi-squared statistic. And what's really important is that it doesn't take into account any model fitting. It really only uses the raw flux density measurements. That's really important for reducing errors induced from model fitting into the variability survey itself. And based on the fact that this is a chi-squared statistic, we would assume that the distribution of the VIP should follow a chi-squared distribution. And indeed, that's exactly what we see. So that's quite comforting as well. So the vast majority of sources are really consistent with just not being variable. Again, that's what we'd expect from a non-variable population, so that's nice. So we can now look at our chi-squared PDF. This is actually not a fit. This is the predicted chi-squared. So it's really kind of comforting to see it behaving as we expect. And we can now make a confidence level cut on this fit to see what is variable and what's not. So we make a 5 sigma cut. Anything above that 58 VIP is classified as variable, and anything below is non-variable. I want to point out in particular, though, the peak spectrum population doesn't seem to follow a chi-squared distribution. In fact, they seem to be a larger bias towards higher VIP. You can see there's a much larger tail compared to the blue master population there. So it kind of suggests that potentially the peak spectrum population is potentially an intrinsically variable population compared to the master population of typical AGN. Okay, so we now have a variable population. Now we have to determine a way to classify the type of variability as well. We saw that it was really quite dynamic and there were lots of different ways it could vary. So that's the measure of spectral shape, or the MOS parameter. And this parameter is really similar to the VIP as well. So it also is based on a chi-squared statistic. And again, it only takes into account the actual flux density measurements, not any model fitting itself. However, it's now comparing the difference rather than the individual SEDs for each year. So to kind of explain that a little further, for this source in particular, if we look down the bottom here, you can see that difference between the 2 years has got quite a lot of structure to it. And so the measure of spectral shape, or the MOS parameter, essentially counts how many points are far away from this median value, and how far away are they. So in this particular case, there are quite a few flux density points that are away from this median value. And so it's got quite a high MOS parameter and is classified as changing its spectral shape. When we compare the entire population, again, it seems to follow a perfect chi-squared distribution, so that's quite comforting. Everything's behaving as we expect. And this is for the non-variable population. There does seem to be maybe a little bit of a shift or a bias excess at around 20 of a MOS parameter, but it's sort of all fairly consistent. We can again make the same confidence level cut at 5 sigma to determine things that are changing their spectral shape versus not. And when we compare with the variable population this time, again, we see that there does seem to be a bias towards a higher MOS value. You can see the peak of that distribution is shifted towards a higher MOS and a larger tail as well. And this is really just indicative that they've already gone through a first level test of variability, and now we're seeing which ones are varying and which ones aren't. So that's sort of just coming out in the distribution there. So if we apply these statistics to our entire population, what do we find? Well, we surveyed, as I said, around 21,000 sources, and we identify over 300 of them that are showing variability across their SED. And within that, we find 51 of them as changing their spectral shape within the 2 years. So here's another example. You can see that's quite a dramatic change in the spectral shape from 1 year to the next. I mentioned earlier that potentially peak spectrum sources may be an intrinsically variable population when compared to typical AGN. So a little bit of a deep dive into that. When we compare the VIP on the y-axis there with the signal to noise on the x-axis, you can see the vast majority of sources in grey, that master population there, are really just a nice flat line behaving sort of as we'd expect. But it's around a signal to noise of 50 where we see that the peak spectrum, those pink points, seems to be complete with respect to the master population. So if we focus in this top corner here, these are sources that are classified as variable, and it seems towards the right of that dotted line, the peak spectrum population and the master population are complete relative to each other. So if we look at the variability of those, thank you. If we look at the variability between those two populations with the VIP in the graph to the right, we can actually see that there is a bias for the peak spectrum sources to not only have a peak shifted towards a higher VIP, but a longer tail as well. And this is really kind of concrete proof that this population, this subset of AGN, is more variable than typical AGN. There's been a few hints towards it in the literature, but this is really the first time we've been able to concretely say it with quite a level of confidence. Okay, so this is, I guess, the big question of the study: what's actually causing the variability? Well, there are three main, I guess, culprits that we could blame it on. Number one is scintillation, so interstellar scintillation, which I mentioned earlier. Number two is potentially all of these sources are just blazars. And finally, the sources themselves could be producing this variability, whether that's due to their own evolution or potentially some unexpected morphology that we hadn't really expected. So if we look first at scintillation, so refractive interstellar scintillation is quite a broadband effect, particularly at megahertz frequencies. You wouldn't expect to see dramatic changes in shape within the MWA band. It's also generally on timescales of years to decades based on where we are in the galactic plane. So we're kind of on the borderline of sampling that timescale. Anything longer would be fine, but at 1 year, it's really sort of on the edge of expected. But an interesting side note for scintillation is if sources are scintillating, it requires that they have a compact component in their morphology of around 5 milliarc seconds. So detecting this scintillation and classifying it is a really great way to get very high resolution images or morphology simply from variability rather than relying on VLBI. But interestingly, if it is scintillation and it does require that 5 milliarc second compact component, peak spectrum sources are not known for having such compact features. So it would mean that there's potentially a bit of a contradiction there as well. So if we look at sort of the suspect number 2, or blazars, still entirely potentially could explain everything that we see. In fact, we actually have known for a while that potentially the changes in shape have been attributed to blazars in the past, because they are quite dynamic and very variable sources themselves. So the changes in their spectral shape can come from a flaring state where we see it flare at the higher frequencies and that flare travel down to the lower frequencies. So we could simply be detecting this flare or this change in state right at the end of the spectrum, and it's already gone through flaring at the higher frequencies. Because these blazars have the jets directed towards the observer, we can see some changes on really short timescales, and we can see extreme variability as well, from whether it's wiggling on its axis or producing a flare in the direction of the line of sight, so we get a Doppler boosting effect. We also know that many variable sources are blazars, and that's actually true for our survey as well. We see a lot of our variable population being known blazars as well. So the final option, or source evolution, or potentially just some weird morphology, there are a lot of ways that you could introduce variability based on the source itself. There's really a lot of parameters in this case. So any one of these could really explain what we're seeing. So the source itself could have, again, a flare going through, and we're seeing the knot interacting with the surrounding medium. We could see dense interactions with that dense surrounding medium. We could see shocks in the jet, re-energizing the plasma, and creating that flare effect in the SED. But essentially, it's a bit of a question mark here, because there are so many different ways that you could introduce intrinsic variability. It's really hard to sort of narrow it down. So ultimately, what's the culprit? Well, in our paper, we conclude for the sources that seem to shift up and down uniformly across the MWA band, well, that's entirely consistent with scintillation. And while there may be other things going on, it's realistically not possible for us to differentiate that. The fact that it's entirely consistent with scintillation, Occam's razor, that's probably what it is. For the sources that are changing their spectral shape, it's really not possible to explain that via scintillation. So we conclude that it's most likely these sources are all blazars. Ironically, if they are blazars, then they're extremely compact and will also show scintillation. So potentially the variability we're seeing is a combination of both the scintillation and the fact that they're blazars. But a big takeaway is that these peak spectrum sources may just have really weird and unexpected morphologies, or maybe these peak spectrum classifications are only temporary, and we need to follow up if we want to be sure that that's what these sources are. So I guess I'll end with my conclusion slide of just highlighting the fact that this is the largest survey of low frequency variability that we've been able to do to date. And as we head into the SKA era, surveys like this are really going to become more possible. And it's kind of a hint that maybe the radio sky is far more dynamic than we expected. So we present statistics to be able to differentiate what is variable, what's not variable, but also try and learn how it's varying as well. And we're currently undergoing a follow-up campaign with the ACTA, MWA and LBA for a handful of sources. So thank you so much. I'll take any questions.
Thanks, Kat. So does anyone have any questions? I have one, but I'm willing to let somebody probably who's more involved in the field ask a question first. So no, great. So I get to ask my question. So for the master population, it like you said, it appeared to, in the Moss parameter, seem to have an excess compared to this chi-square that you modeled. Is that indicative of some sort of statistical artifact, or do you think it's actually indicative of maybe some science?
Unfortunately, it's not science, I think. It would be cool if it was. I think it comes down to the fact that the Moss parameter is a lot more sensitive to an individual point being away from the median. It picks that up as being a change in shape, whereas the VIP is a bit more robust to individual variations within the band. It kind of relies on all 16 points changing. So I think that excess there is purely just a statistical, there are anomalies within the band that it's still not quite high enough, but enough that we can see a bit of a bias there. And the MWA in particular, because you have the sub-bands, which are 4 individual points, you can often see 4 points moving up and down. And so it's not really true variability, it's coming from the the instrument itself.
Yeah, that makes sense. So if you have any more further questions for Kat, please ask her in Slack or on the Q&A. Thanks, Kat. Thanks again. So we will move on to our next speaker, Christina Nyland. If you want to go ahead and share your screen and unmute yourself. Christina will be talking about compact radio jets revealed by commensal V-light observations. So I know Christina had some technical difficulties earlier, so I'm hoping everything, yay.
All right, are we good?
Yes, we're good.
Okay. Well, thank you very much, Nichole. And thank you to the organizers for this opportunity. So again, my name is Christina Nyland, and I'm an NRC fellow based at NRL, which is the U.S. Naval Research Laboratory in Washington, D.C. And today I'll be talking to you about compact radio jets. So I hope you really like compact jets and peaked radio spectra and SEDs, because we're going to see more of them. But I'll be talking about an instrument we haven't heard as much about, known as V-light. And I'd like to emphasize that this work has benefited from numerous collaborators, including the people listed at the bottom of this slide who've been crucial for this, and also the NRL Remote Sensing Group. So I don't think I need to convince this group that active galactic nuclei are cool, but just for completeness, AGN are the result of accreting supermassive black holes, and they're among the most energetic objects in the universe. And a subset of them, I would argue the most interesting ones, about 1 to 10% of them, are able to launch powerful jets of radio plasma that can reach sizes of hundreds of kiloparsecs or even megaparsec scales. And so these large-scale extended radio AGN, they extend far beyond their host galaxies, and they can affect the intergalactic medium and the intercluster medium as well. And I've shown a couple of radio optical and X-ray composite images of two famous examples of radio AGN. And in addition to being really interesting objects in their own right, I just want to emphasize that jets and lobes are important because they play a role in galaxy evolution. They're able to actually heat, disrupt, or expel material in their paths, and this potentially leads to galaxy scale feedback, which can alter future star formation. So as interesting as large-scale AGN jets and lobes are, not all radio AGN are able to reach large scales. So some of them, they never make it past the confines of their host galaxies for various reasons. And so they have extensive kiloparsec scales or smaller. And I'd just like to talk about these sources a little bit. What would make them compact? So explanations, Catherine Ross already presented some of this, but explanations can include things like projection effects, as is seen among blazars, which are AGN jets pointed directly at us. And then there can also be physical effects as well. This includes things like propagation effects due to plasma lensing, like scintillation, or you could have actual intrinsic variability. You can actually also have a compact size due to user confinement by a dense ISM. Jumping ahead to variability here, because I'm so excited about this session. So on this slide, I'm showing a couple of artist illustrations that are based on a study I've been leading that focuses on AGN that have transitioned from being radio quiet in the first survey to then being radio loud in VLAS about 20 years later. And so there was recently a paper on this work, Nyland et al. 2020. It was posted to the archive 1 week ago. And there were some nice press releases by NRL and NRAO who made these beautiful images. Now, these sources, we think that they're prime examples of AGN jets that are powerful but compact. And I invite you to check out the paper. So we know that compact jets exist, and we're finding new ways to identify them, but there's still a lot we don't know. And it really boils down to just the sheer observational challenges of resolution and sensitivity. So there are fundamental questions that we haven't answered yet, like how common are compact jets? How do they evolve as a function of redshift? And what role do they play in influencing galaxy evolution? So clearly what we need is a large statistical analysis of compact AGN jets. And I've been very excited watching all of the progress that's been made with surveys like GLEAM using the MWA in recent years. But I'd just like to highlight the challenges to make them really clear here once again. So why is it hard, and how you find them? So you can identify them based on their morphologies. So this is directly resolving them down to kiloparsec or even parsec scales. And this requires high resolution imaging, often using techniques like VLBI or very long baseline interferometry, which is observationally expensive. Another way of identifying them is through spectral curvature. This is because they have those characteristic peaked spectral shapes, which arise due to absorption physics. And I'll talk more about that in the next slide. And then there's also variability, which we heard, a really nice talk by Catherine Ross just before this one. And so variability can arise due to effects like scintillation or other propagation effects, or you can have intrinsic mechanisms like flaring, or for the youngest jets, they can actually you can actually have source expansion as the jet grows. Okay, so spectral curvature is really important for this talk, so I'll explain it a bit more here. The diffuse lobes of extended radio galaxies, like the example shown here on the left, which is Centaurus A, they're optically thin, and so their radio emission follows a simple power law shape. And it takes millions of years for extended lobes like this to form. Now, on the right-hand side, I've got a young source for comparison. And these objects typically have ages of thousands of years or less. And they're compact and affected by absorption due to high electron number densities. And here I've plotted just a simple single component and synchrotron self-absorption curve, just to really highlight the difference in spectral shapes of these two classes. So keep this in mind if this hasn't already been made clear in the previous talks. And I just threw this in at the last minute. These are the spectral shapes of the young AGN that appear to have turned on in the time frame between FIRST and VLAS. So please visit the recent paper, Nichole et al. 2020, for more details on this. I just threw this in because it seemed like this crowd was really interested in these types of figures. So I want to highlight, I wanted to focus on some nice examples here of real radio spectra from a project that's being led by a PhD student from the University of Virginia, Pallavi Patel. And she's actually defending this work as part of her thesis in, I think, like 36 hours. So everyone should send her good thoughts. She's doing really cool work. So this study of hers focuses on compact radio AGN hosted by dusky quasars. And it combines data from a variety of radio surveys. And that's shown on the flux versus frequency plots here, as well as subarc second imaging with the VLA. And the sources here highlight curved radio spectra in the top row of somewhat intermediate scale sources. So you can see they have pretty mild level of curvature here. It's not super obvious. These are kind of, I think of them as teenagers. They have sizes of several kiloparsecs, so they're not quite young sources, but they're also different than old evolved power law sources. And then on the bottom is a more classic example of a source that likely has a curved, likely has a peaked radio spectral shape and a compact morphology. Okay, so here I've plotted some synchrotron self-absorption curves with peak or turnover frequencies that increase from the megahertz domain in red, shown here, and then to the tens of gigahertz domain in blue. So this is meant to be a cartoon plot. It's inspired by Joe Callingham's 2017 paper. I think he has a figure very similar to this. And so it's meant to just illustrate that the turnover moves from high to low frequencies as a young source expands and gets older. So I haven't taken into account things like redshift, which is also very interesting, and we heard about in Jess Broderick's talk. That's future work to do after this meeting. So I've also overplotted some popular surveys, some well-known surveys. I don't have time to describe them all, but they span a wide range of different observing frequencies. They have different sensitivities, different resolutions, and they were conducted at different points in time. And the big takeaway is that no single radio survey can really capture the full population peak spectrum sources. Their spectral shapes are very different, and you can catch a source. You can catch it in this optically thick part here, which is important for characterizing the shape. You can catch it in one survey and miss it in another survey that's not even at that much higher frequency. So you really need to take into account all the available information from surveys, and we need to overcome challenges in differences in resolution and depth. So I'd like to now highlight prospects for in the sub-gigahertz domain with an instrument we haven't heard as much about. This instrument I'll be focusing on is called VLIGHT. And VLIGHT stands for the Very Large Array Low Band Ionosphere and Transient Experiment. So VLIGHT is a commensal 340 megahertz system operating on 18 antennas of the VLA. And the word commensal here means that it operates at 340 megahertz simultaneously with regular VLA observations at higher frequencies. And since it piggybacks off the VLA, VLIGHT can reach up to 5 arcsecond resolution when the VLA is in the A configuration. So this combination of frequency and resolution makes it a potentially attractive tool for identifying and studying compact jets. And if you'd like to learn more about the technical details of VLIGHT, I encourage you to attend the talk by Wendy Peters on Friday. And also there was a very nice lightning talk by Surya Bethapudi on VLIGHT Fast. Now, VLIGHT collects a huge volume of data since it's basically recording on the VLA almost all the time. And it celebrated its 6th birthday last week. And at that point, it had reached a benchmark of 37,000 hours of data. And so this is a plot of the sky coverage of VLIGHT from its 6th birthday. And you can see a lot of the sky has data, and there are also a lot of patches of sky that have deep data. So there are a lot of areas that have, shown in red, that have at least 24 hours of data. Some parts of the sky have hundreds of hours or more. And one patch of the sky that's been really interesting as sort of a test bed is based on some VLA observations that targeted the Hubble Ultra Deep Field. And with VLIGHT's field of view, they sort of capture this larger Chandra Deep Field south that encompasses it, if you're familiar with the hierarchy of extragalactic deep fields. In any case, there's about 150 hours in this area. So it's a really nice way to sort of test VLIGHT and verify it by doing science. So here's the latest deep VLIGHT image of this CDFS field. And the field of view is 2 degrees. And this image has an RMS noise of 160 microjanskis per beam and achieves a resolution of 10 arcseconds. And there are 668 catalog sources. So the imaging, this is an image plane combination of 6 different images spanning about 21 hours, by the way. The imaging has been led by Wendy Peters and Simona Giacintucci, and then the primary beam modeling is being led by Emil Polisensky. So a key update from SALF 2019 that I'd like to emphasize is that the deep image shown here now includes primary beam corrections. And I don't have time to go into this in detail, but this is a really exciting step forward, given the challenges posed by the unique optics of VLIGHT. So just really quick, the deep VLIGHT imaging in CDFS, it benefits from a lot of multi-wavelength data. This includes deep radio imaging from surveys like ATLAS at 1.4 gigahertz that has similar resolution to VLIGHT in this field, and lots of infrared, optical, X-ray, et cetera, data. And if you're interested in this sort of multi-wavelength stuff, I encourage you to check out the Spitzer Deep Drill Survey paper led by Mark Lacey, and that just appeared on the archive on Monday. So check that paper out if you're interested. A key thing that we gain from all of this multi-wavelength data when we're doing our testing of VLIGHT via doing science, we've got photometric redshifts available from all of the infrared and optical data that we have. So this is actually some work that I led a few years ago. We have force photometry for 800,000 sources covering 4.5 square degrees in CDFS. And you can read more about the strategy used to accomplish that in Island et al. 2017b. For the VLIGHT CDFS catalog, we've got redshifts for 66% of sources. And this includes a few redshift candidates as well that I'm working on investigating to see if any of them could be real high redshift radio galaxies. So this slide shows a radio color plot of sources in the deep V-Light CDFS image. So if you're not familiar with these kinds of plots, a color plot just shows two different spectral index measurements plotted against each other, and you can use it to sort of pick out different different types of sources that have different spectral shapes. So in this plot, I'm showing the spectral index between TGSS at 150 megahertz and V-Light for alpha low, and then alpha high is V-Light and Atlas at 1.4 gigahertz. So there are a lot of technical details and caveats I've swept under the rug that we can talk about in the coffee session. But what I'm really interested in is answering the question, are there any peak spectrum sources that V-Light picks out that we didn't know about before from other surveys? And the answer seems to be yes. In addition, if we colorize these points, it's the same plot, just colorized by redshift. We find candidate peak spectrum sources in the sample tend to have redshifts around 1 to 2, which is an interesting period of cosmic history. Okay, so are those candidate sources that I showed you real? The answer is yes, we have some really promising candidates. So here's an example faint megahertz peak spectrum source identified by V-Light that we didn't know about before. This is a redshift 0.9 source. It has very nice spectral shape. It could be either synchrotron self-absorption or free for absorption. We would need deeper low frequency, high resolution data to reach down there. But it is compact on arcsecond scales, as you can see in V-Light and the higher resolution Atlas and VLAS images at 10 arcseconds and then 2.5 arcseconds. It's also detected in the GLEAM wideband image, but not the individual bands, by the way, for people who are interested in that. So just real quick in the time I have left, another sign that this source is compact comes from some preliminary evidence we found for variability. We already know from previous talks in the session, variability is common in association with compact sources. And we think that we are still verifying this, so stay tuned for further details. And I apologize for racing through this, but if this is something that interests you, let's talk about it at coffee. And lastly, I just want to show the turnover size diagram. This relation arises because of the evolving radiospectral shapes of expanding sources. And so the faint megahertz peak spectrum source found by V-Light, if you put it on this diagram, its rest frame turnover of 428 megahertz corresponds to a size of 2 kiloparsecs. And so it'll be a lot of fun following this source up and other sources identified by V-Light to see if they fall in the relation, and if they don't, it could imply some interesting absorption physics, as was argued in this very nice paper by Keim et al. 2019. So with that, I'll end by emphasizing that there are lots of really new, exciting radio surveys probing new domains observationally, and we're going to find lots and lots of peak spectrum sources and understand how young and compact jets grow. But we need to remember that no single survey has all the answers, and we need to find ways to combine them. And deep commensal data from V-Light can help add to the story. And so that's all, and I'll stop there, and thanks for your attention.
Thanks, Christina. Do we have any or any questions for Christina?
I've used my privilege as a panelist. Really fascinating talk, Christina. Obviously, I'm very engaged by this science topic. I just have a few. Maybe I'll just start with the first one that's a little bit different. So you're interested in, obviously, AGN evolution and variability. The one that we saw in GLEAM that grabbed me that I didn't expect were these peak spectrum sources that then show an uptick at the end there. And my hypothesis was that we're just seeing multi-epoch activity, right? And we're seeing a different regime. Have you identified these? It's a bit, GLEAM was nice because I probably wouldn't have believed them with a single point, right? But still, with that knowledge that they exist, have you seen something with V-Light, that looks like a peak spectrum sources at higher gigahertz, and V-Light's a bit higher than you'd ever expect? You have to be careful that you're not being dominated by flat spectrum sources, but I was just wondering if you've considered that problem.
So I've been focusing on the peaked and inverted spectrum sources, sources that behave in other weird ways. They are interesting. They could be restarted sources. But then again, you could also have issues with resolution, mismatch between surveys that are difficult to account for unless you do some kind of follow-up to check at higher resolution. So it is of interest, and it's a great question. I'll look into it more.
Yeah, and you also got the resolution with VLAS and stuff that you could actually start to answer these questions. Obviously, you're probing different emission at low frequencies that you might not pick up, so it's difficult, but still very, very interesting to ask.
I think a key thing that I've concluded, especially when it comes to using VLAS, because VLAS quick look images, they don't look the greatest. They're a little rough. There's a lot of side lobes everywhere. It's hard to develop heuristics that will cleanly separate out all the interesting sources without having a bunch of junk. So if you can keep the number of objects in your sample manageable, which I don't know what that means. For some people, maybe that's 10, 100, maybe thousands. I don't know. Some people are looking at thousands, but I think it's important to look at them, and we need some human vetting. So look at your images, I guess.
Totally.
Is what is important.
All right. Is that it? Or I've got another follow-up question, but I can take this further.
Yeah, just take it to the coffee talk.
No, yeah, I'll take it to coffee talk.
Great. So our last talk of the session is by Virginia Cuciti. She will be talking about radio halos moving towards large samples for galaxy clusters. Now, it's very, very early for Virginia right now, so she's opted to do a recorded talk.
Sorry, I'm just going to set this up now, Virginia. I just have to make sure you hear me fine because it is a little bit finicky. And let me just talk. And hopefully everyone can see that. Now, if I hit play, Nichole, can you just confirm you can hear it?
Hello, everybody.
Yes.
First of all, I would like to thank the organizers for giving me the opportunity of talking about this work. I will talk about radio halos. In particular, I will try to explain why we really need to move towards large samples of galaxy clusters to study radio halos. This is the outline of the talk. I will start with a brief introduction on radio halos in galaxy clusters. I will also give you an oversimplified theoretical background. The large majority of the talk I will spend talking about the mass-selected sample of clusters that we observed with gigahertz frequency observations and the results that we got from this sample. And in the last part of the talk, I will tell you what we are doing and what are our plans with LOFAR. So radio halos are these cluster scale diffuse sources that are usually found at the center of merging galaxy clusters. In the theoretical scenario, they form when turbulence is injected in the intracluster medium as a consequence of a merger event. In this theoretical framework, radio halos are expected to form with different spectra, in particular with different break frequency or steepening frequency. The steepening frequency is directly proportional to the energy involved in the merger, which means that it's proportional to the mass of the clusters and to the type of merger, so whether it's a major or minor merger. So basically, massive galaxy clusters undergoing energetic merger events form radio halos with high noise, observable up to gigahertz frequencies or even higher. But there are also less energetic merger events, less massive clusters, that form radio halos with very steep spectra, the so-called ultra-steep spectrum radio halos. So the first expectation is that in general, the fraction of clusters with radio halos should increase with increasing the mass of the host cluster. Also, because of the presence of ultra-steep spectrum radio halos, when we observe at low frequency, we expect to see an increasing fraction of clusters with radio halos. Of course, in order to test these expectations, we need large samples of galaxy clusters. And it would be nice to have samples selected in mass, because the mass is the key parameter of the model. It's what is the parameter that tells you the amount of energy that you have available for particle acceleration. So today it is possible to select almost mass-selected samples thanks to facilities like Planck that survey the sky via the Zunayv-Zeldovich effect. So with this idea in mind, we compiled a mass-selected sample of galaxy clusters with deep radio observation to perform an unbiased statistical study of radio halos. So we started from the Planck cluster catalog. We selected clusters with mass larger than 6 times 10 to the 14 solar masses in the redshift range 0.08 to 0.33. We ended up with 75 clusters. They are more than 80% complete in mass. And we observed them with the GMRT or with the JVLA. So now each one of these clusters has information coming from deep radio observations. Now, I won't tell you basically anything about the data analysis. I would just like to summarize what we found in these clusters, combining our new observations and previous literature information. So we have 75 clusters, again, 28 host radio halos, 10 of them are ultra steep or candidate, ultra steep, 7 clusters host relics, 10 host mini halos. Then we have some candidates, 5 candidates radio halos and 1 candidate mini halo. And 31 clusters do not host diffuse emission. For the majority of them, we were able to derive upper limits to the radio power of the diffuse emission. So now let's go straight to the statistical part. And we start with this diagram, which is called morphological diagram, where you see the concentration parameter versus the centroid shift. These are 2 parameters coming from the analysis of X-ray Chandra data. And they are very powerful to tell us something about the dynamical status of clusters. So basically in this plot, we have relaxed clusters in this region here on the top left panel, and then clusters become gradually more disturbed going towards the bottom right. So the first information that we have here is that more than the 90% of radio halos, which are the red dots, are found in merging clusters, while only 2 are found in relaxed systems. Another thing that we see is that non-radio halo clusters, the black dots, can be either in relaxed or merging clusters. But we can do another thing here. We can split this diagram into 2 mass bins. So here we have high mass clusters, here we have low mass clusters. And what we learn is that in high mass clusters, we have only the 20% of merging clusters without radio halos, while in low mass systems, we have 75% of merging clusters without radio halos. So this is really telling us that the formation of the radio halos is a combination, is an interplay between the mass of the cluster and the merging dynamical status. Now let's move to the radio power mass diagram. In this plot, we have the radio power versus mass of radio halos, ultra steep spectrum radio halos, and upper limits. In this plot, we actually added some clusters from the literature. I don't have time to tell you why we did that. If you are interested, of course, I can explain during the question session. So we fitted the radio power of these radio halos using the BCS-YX method. These are the best fit parameters. This is the correlation. We can see that almost all the upper limits lie below the correlation, as it was previously found in other works. And this is the scatter of the correlation, 0.31. It's quite large, but this is kind of expected, because here we have to imagine that during the lifetime of a cluster, clusters travel across this diagram. So for example, a cluster could start here in the region of the upper limit as a relaxed cluster, and then a merger event comes and the radio halo lights up, so it goes somewhere here, and then the merger finishes and the radio halo fades away and the cluster goes back here. So this plot here is just a picture of a complex mix of galaxy clusters in different merging status and in different life stages of the lifetime. So we try to investigate whether the scatter of the correlation can be somehow related to the dynamical status of the clusters. So in this plot, we have on the y-axis the distance from the radio power mass correlations. So these clusters here are above the correlation. These clusters here are below the correlation. On the x-axis, instead, we have a measure of how much the cluster is disturbed. Actually, what we have in the x-axis is the distance from this bisector here. So these clusters, these relaxed clusters are here, and then clusters are more and more disturbed going to the right. So what we learn from this plot is that the radio halos that are scattered up with respect to the correlations are those found in the most disturbed clusters. At the same time, the radio halos that are below the correlation tend to be in more relaxed clusters. So the answer is yes, the scatter of the correlation is at least partly due to the different dynamical status of the clusters that we are looking at. Another step that we did is not only to look at the radio power of radio halos, but also at the radio emissivity of radio halos. The radio emissivity is basically the radio power over the volume of the radio halos. And it's a very important parameter because it allows us to remove the dependency of the radio power on the size of the radio halos. Now, again, I don't have time to tell you how we exactly calculated the emissivity. This is the equation that we used. The E0 is the central surface brightness of the radio halo. The RE is the E-folding radius. And these two parameters come from the fitting of the radial profile, of the surface brightness radial profile of our radio halos. Here you see the emissivity versus the mass of the clusters for radio halos and upper limits. Of course, for the upper limits, we didn't fit anything, but since upper limits are done injecting a mock radio halo into the data, this mock radio halo have some parameters that we choose, so we know the E0 and RE for the upper limits. Here in this plot, we see that there is a hint of bimodality also in the radio emissivity mass diagram, with upper limits that lie at least 5 times below the bulk of the radio halos. I say at least 5 times because, of course, remember, these are upper limits, so it might be that they are not clustered here as we see, but they may be distributed farther below this point. Another thing that we did was to calculate the fraction of clusters with radio halos as a function of the cluster mass. This plot is very dense. I will try to guide you through it. I won't mention everything that you see on this plot. So we split the sample into 2 mass bins, the high mass bin and the low mass bin, and we measured the fraction of radio halos in the 2 bins. We found that in high mass clusters, we have about 75% of radio halos. So you can concentrate on this black dashed line here. In low mass clusters, instead, the fraction of radio halos is about 35%. So for the first time, we were able to detect this drop in the fraction of radio halos going from high mass to low mass systems. We wanted to compare this observed drop with the expectations of turbulent acceleration models. So we used this model from Cassano and Brunetti 2005 to calculate the expected fraction of clusters with radio halos as a function of the cluster mass. First of all, let's focus on the red line. The red line is done with steepening frequency greater than 600 MHz, because our observations are GMRT and VLA observations, so this is the frequency that we have to compare with. And I would say that there is quite a good agreement between our observed fraction of radio halos and the one predicted by the model. Now, what happens if we want to calculate the expected fraction of radio halos with steepening frequency larger than 140 MHz, so at lower frequency? This is the blue line. So what we see here is that in the low mass bin, there should be a much higher fraction of clusters with radiohalos that we are currently not seeing. These are all the ultra-steep spectrum radiohalos that are only visible at low frequency and that we do not detect with our higher frequency observations. This is also in line and connected with what I was saying before. So in the low mass clusters, we have a high fraction of merging clusters without radiohalos. So those are the best candidates to search for these ultra steep spectrum radiohalos. So let me summarize and conclude this part before I move to the last part. We selected the largest mass selected sample of galaxy clusters with deep radio observations. The main statistical results that we found are that more than the 90% of radiohalos are found in merging systems. We updated the radio power mass correlation, and we found evidence that the scatter is at least in part driven by the different merging status of clusters. For the first time, we studied the emissivity mass diagram, and we found a hint of bimodality in this diagram too. And we showed that the fraction of clusters with radiohalos drops in low mass systems in agreement with the prediction of turbulent reacceleration models. So what's next? As I said, the existence of a large population of ultra-steep spectrum radiohalos only observable at low frequency is the main prediction of the turbulent reacceleration model. However, this prediction has never been tested so far, mainly because we didn't have sensitive low-frequency observations. For the same reason, there are no statistical studies in the low mass end of this plot. And also there were no statistical studies at high redshift. So this is going to change in the near future because thanks to LOFAR, we now have low frequency sensitive observations. So what we are doing now, together with the LOFAR collaboration, is selecting all the Planck clusters in the data release 2 of the LOFAR 2 meter sky survey, so at 140 megahertz. We are talking about more than 300 clusters that you see in this plot. We now have all the high and low resolution and source subtracted images. We also did the optical and X-ray overlays for those clusters that have X-ray observations. And we are now in the process of classifying the diffuse emission that we see in these clusters, which seems a trivial point, but it's actually not so straightforward. The idea that we have is to split this large sample into statistically meaningful subsamples. And for example, here we can imagine a relatively high mass, low redshift sample where we can basically perform again all those studies that I've shown so far. So we can study the occurrence of radiohalos as a function of mass and dynamical status. We can do all the correlation, radio power mass, radio power X-ray luminosity at low frequency. And we can do for the first time the statistical spectral studies. So we can compare with higher frequency observations, for example, GMRT and DLA, but also with lower frequency observations, so with the LBA at 50 megahertz. Then we will also do the first statistical studies at very low mass and at very high redshift. Here I won't say anything because Gabriella Di Gennaro will talk about this in the next session. Of course, this huge sample not only allows us to study radiohalos, but also we can do the statistics of relaxed clusters and mini halos. We can do the statistics of relics and fossil plasma sources, and also the cavities and AGN feedback. Thank you.
Thanks. Thanks, Virginia. Do we have any questions for Virginia? I had a quick one. I was wondering if you have to do everything by eye for such a varied sample, like this, like particularly with the diffuse emission? You said that, you know, that's difficult. Is this a fully like by eye type of verification that you need to do?
So yeah, I think in this respect, this sample is very instructive because, you know, 300 clusters are still borderline. So you can actually, they are a lot, but you can actually watch every single image. It takes time. It is taking time also because we are 4 people and we want to do it separately to be less biased as possible. But still, it is doable. The fact is that this is only the DR2, the data release 2 of LOTS, and it's like a tiny percentage of the area that LOTS will cover in the next years. So this will not be doable at all in the next data release. So we are already thinking about ways to do that, but we don't have a solution yet. So yeah, so far the classification is done by eye, watching every single image and saying, okay, here we see some diffuse emission, this is large enough to be called something. Then the next point will be where we see diffuse emission, central diffuse emission, that we think may be a radio halo. Then now we have a script, an automatic script that fits the radial profile of this emission and tells us the radio flux, the size. So that is already automatized, and it's not only important, the automatization of this part is not only important for like saving time, but also because there is no bias, for example, given by the RMS of the map. So we are not saying, so previously we used to say the radio halos is, I don't know, 500 kiloparsec because we were really measuring the 3 sigma contours. This will not be done in this sample. But yeah, the next step would be to find automatic ways to actually classify the diffuse emission, which is not, of course, it's not trivial, as I was saying before.
It sounds like a hard problem.
Yeah.
Do we have any last minute questions for Virginia?
I think I'll just ask one, Virginia. Thank you for getting up to answer the questions live. I really appreciate it. Are you trying to use the in-band spectral indices of LOTS yet in terms of helping you define the shapes and structure of these things and help identify them?
No, we haven't tried that so far because, yeah, we think it's a bit, it's not enough to, so the pivot in frequency is not enough. So I think we will do the spectral study as a second step. We have already a lot of data. We gather a lot of data with the UGMRT and we have a lot of data with the LBA, so it's doable. It's gonna be, again, a lot of work because those data are not ready yet. But I think for the spectral studies, we will wait for other frequencies.
Okay. Cool. Thank you.
You're welcome.
Awesome. Thanks. So that wraps up this session. We are going to go over to a coffee tea room for some informal chat and for catching up. Joe will post the link, I assume, on Slack, but if you want a quick link, I just posted it in the chat as well. So I hope to see you guys there.
Yep, come and join coffee and tea time if you feel like it. Okay, see you soon, guys. Bye.
Yep, see you.